Our fourth speaker and last speaker of the day today is Wolfgang Wagner. Wolfgang is from the Earth Observation Data Centre at the Technical University in Vienna. Wolfgang just experienced a fire alarm, so he had to leave the conference, but luckily that's all over and he's back to provide his presentation. And his presentation is titled the CEMS Global Flood Monitoring Service, From Science to Operations. Wolfgang, go ahead.
Thank you, Albert. Thank you for the introduction. So it's exciting times and I'm really happy that I'm back from this fire alarm. So before I start my presentation, I really would like to thank all my co-authors from the Technical University of Vienna, from LIST, from DLR, from GMA, GUL, and the UDC, who have been working on that system. So what's the idea behind this monitoring system? As you know, Sentinel-1 is a fully operational mission that consists of 2 satellites that provide systematic coverage at C-band with 20 meter spatial resolution. It has originally not really been foreseen for doing operational near real-time applications over land, but more over the oceans. But obviously, it's, you know, with the progression of the mission, things have been improving importantly. So the idea of this service is to have fully automatic processing of all incoming Sentinel-1 scenes within the shortest available time period, since when the data become available, and to do an ensemble of 3 flood mapping algorithms so that we get an idea of where potential flood areas are. And as you will see, it's a pretty complicated data product. It consists of several layers, including a flood extent map, an uncertainty map, with various exclusion masks and advisory flags. Here in this graphics, you also see the roughly the repeat coverage of Sentinel-1. So in some areas, like here in particular in Europe, it's excellent in the order, say, from 1 to 3 to maximum 5 days. But if you go in other areas like Siberia or the northern parts of Canada, there's for various reasons a very poor coverage there. Simply then, you know, getting these images is not easy. So what we've developed overall since many years here at TU Wien in cooperation with our partners, that we've established a processing architecture where we have the essential element is a data cube. So essentially, we do most our scientific analysis within this offline processing system, where you can do, for example, a model calibration, or you can do machine learning, and then you get your algorithms. And then you can also move it to a near real-time data flow, where you have incoming Sentinel-1 backscatter images, you do pre-processing, then retrieval, and then you get different level 2 data products. Our first data product has been soil moisture, and here we strive to do something, a flood alert data product. The data cube system we use is kind of very bare metal data cube system, where we have defined a global gridding system with 7 continental zones, but we call it the AQ7 grid. You see here the example for the how the North American grid is being tiled up in our system. And through this, we do the pre-processing of all the incoming data, and with this, it's possible to access data very fast in time. Just to give you an impression about what kind of pre-processing is applied to the Sentinel-1 data, we use as the core element the open source software from ESA, the SNAP software, or called also Sentinel-1 Toolbox. But along with this, we also use individual modules. For example, we've developed improved border noise removal technique, and then obviously we have our tiling system. By the way, if you're interested in the AQ7 grid system, that's open source, so you can also use it for your purposes. On the right graphic, you see the order of magnitude of data volume that we are dealing with. So the unfortunately, I don't see it myself because there's wait more. So now I see. So you see for the different years, 2015-16 has been just Sentinel-1, and with the addition Sentinel-1A, and with the addition of Sentinel-1B, there's a significant jump in the data volume that has also been increasing in recent years as ESA is continuing to optimize the mission. So when you consider the years 15 to 20, the data volume of the raw interferometric wide swath GRD data already makes up 1.4 petabyte. When we go to the Sentinel-1 data cube, initially we also worked with 10 meters, but we decided to go to 20 meters, just also for pure data volume reasons. So you see that there's a substantial reduction in the size of the data, but still we are dealing with tens of terabytes in the processing, or hundreds of terabytes. So it's a very demanding system. So what we've created is we have created a tiered storage system containing of very fast disks connected to a high performance computing facility, where we have the Vienna Scientific Cluster 3+ and 3, where we did most of the processing so far. Here's already a question. Shall I also already say this?
Feel free if you want to. You can. Yes, you can if you want.
Yeah, we went for the 20 meter because the 10 meter resolution is still very noisy still. And at the 20 meter, obviously, much of the spec is already suppressed. And it's also, of course, a matter of data volume. So handling the system becomes more easily manageable. That's the real reason. Yeah, so do we do offline analysis and over large scale here on a high performance computing platform? We do individual scientific analysis on a cloud platform. It's an OpenStack account, and we have now set up a dedicated cluster for the near real-time operations here in a separate location to make sure it's running all the time. In terms of the algorithms we are using 3 very different algorithms, one implemented by our colleagues from DLR, one by our colleagues from the Luxembourg Institute for Science and Technology, and one from our group, whereby the algorithm from DLR is an image-based classification technique using fuzzy logic with post-classification and reach growing. LIST is using a change detection using hierarchical split-based approach, and our approach is a Bayesian classifier informed by the full per pixel Sentinel signal history. So really 3 very different algorithms, and essentially we look for a maturity mode in the flood extent. In each case, we also derive uncertainties, so we have an average of the uncertainties that comes out. I'll just give you some insight into how our algorithm works. So you would have here a backscatter time series in red. What we do is to understand for each pixel location, we basically fit into the time series a harmonic model so that we can account for seasonal fluctuation in backscatter. And this information is available for each 20 meter pixel. And then we have one signature that characterizes a typical open water surface. That is, of course, is the same everywhere around the globe because water doesn't change its backscatter characteristics. And then we match for each individual pixel. We match the 2 probability distribution functions, and we look for the value. For example, this value here would be situating here, so this would be a clear non-flood pixel, and here this would be a pixel where there's water. Here you see this as an example from a Greece test site, how this variable backscatter reference image that we have created in this way, for example, looks for winter and how it looks for summer. So there's obviously changes, particularly in the agricultural areas, reflecting the growth of vegetation and also reflecting changes in the soil surface roughness. Many land surfaces can be very well described by this harmonic model, but coming back to these agricultural areas, there this harmonic model, this simplification that we assume that each pixel carries the same seasonal signature from year to year is sometimes not fitting, with the effect that sometimes our reference image isn't good. That leads, unfortunately, of agricultural areas to an over-detection in the case of our algorithm. So this could be, for example, fields that have recently been plowed and that are very bare soils and smooth soils that may have similarities to a water surface. So this is very hard to deal with these kind of surfaces. Just give you an example of a recent flood situation in Central Europe. Here, this is from the big flood in Germany in July 2021. And here we took the example of the river Aisch in northern Bavaria. This is the Sentinel-1 backscatter image in vertical polarization. You see in this case, the flood is very nicely visible in the image. But you also see that on the side, there are many other black areas that are difficult to judge what they actually are. And if you look into the harmonic mean reference image, you will see that there are some areas that have this characteristic low signatures. So these could be permanent water bodies. So after our algorithm, we get this flood extent map, but you see on the side there are also some possibly misclassifications, remaining problems. So to deal with as good as possible with the challenging situation that we do a fully automatic flood mapping without having manual interaction. We provide as good as possible reference information to tell users and ourselves. Actually, these are areas where we cannot expect that Sentinel-1 can provide information, or where there's a certain where we can expect quality problem. So we have defined 4 layers. One is called a no sensitivity layer. One is called low backscatter layer. One is called the topography distortion layer, and there's a radar shadow layer. We also want to do advisory flags that deal with the problem. That's, for example, if there's wet snow or wet ice, that this can look very much like open water. And there's also, of course, situations where we may not be able to detect water because it's too much wind. So all of these things are very difficult to deal with because we lack the information at the required spatial resolution and timeliness to actually do a masking. So we will try to provide advisory flags. Yeah, so just to give you information, for example, we have now established all these global masking layers. So the no sensitivity layer, we combined basically a vegetation layer and an urban layer. I've got a question online. With the Somrush, have you also considered not to try to fix all issues in your own methods and instead rely on the other methods? Well, I think all methods have the same, because essentially what we're trying to fix is the limitations of the physical measurement system of Sentinel-1. So all flood mapping algorithms, as long as they're based on the backscatter amplitude, will face the same issues. So as I said, the no sensitivity layer, if you have a dense forest, you will not be able to see through the ground. If you have urban areas, we also have big troubles. And we've seen in the presentations before, there it may be advisable to use side interferometry to be more reliable. Yes, with sand is a very difficult issue, particularly if you go to desert areas. So we call this the low backscatter layer. As we have the data available, we look for those areas that have overall throughout the year a consistent low backscatter, and we do provide masking of those areas. It can also be lookalike areas. It could be, for example, airports that have a very low backscatter that are identified in this way. So this, for example, we consider areas where backscatter over a long time is smaller than -15 dB to be these low backscatter areas. Here's just an example from Germany, where we see just open water surfaces in this case. Of course, going into topography is also a problem with SAR, as everybody working with SAR is like. So we try to map areas that have rugged topography. We use for this a hand index based on the SRTM hydroshed data set, and we apply a certain masking to make sure that we are not identify water in topographic areas. And last but not least, we also try to identify radar shadows, which is very difficult because a radar shadow could be behind, for example, forest. And the radar shadow is basically being produced for each individual orbit, and we are trying to match ascending and descending orbits. So this method works very nicely when we have good coverage. We struggle with that method if there's only like 1 or 2 Sentinel-1 orbits covering an area. And then we basically have to hope that these shadow areas are being covered by the low backscatter map. I have 3 test cases with me. I only show you now in the presentation here one. Maybe if you're interested in the other cases, Greece and Myanmar, I could show it afterwards. So here would be now not just our algorithm, but the algorithm from DLR and LIS and ours, and how they would see the flood extent. It's difficult to judge which areas are really flooded and where we, for example, have false positives. But basically, like if the algorithms are successful in working for a certain area, we often see rather good correspondence. For example, the dark red colors are where the 3 algorithms agree, and the light one would be where just one algorithm indicates here's flood. And now there could be different situations of how you say, well, here's flood or no flood. Yeah, so with Myanmar case I can show later, because there, for example, we have a deviation between the 3. Yeah, and here, for example, would be an ensemble that we put together. It's certainly, I hope from the presentation you already got a feeling how challenges this is from a production side. For us, one of the big challenges has been that we have been asked to move from the SLTM processing to the Copernicus stem. So we had to adopt the Copernicus stem to enable processing within SNAP, and we did a full reprocessing of the complete archive. It also turned out, because many algorithms are running on individual Sentinel-1 scenes, and we are working with this data cube system, and switching back between a data cube and in images is not a simple thing, so that has complicated matters. I guess you can also imagine that such a system with rather long pre-processing and then 3 very different algorithms, it's quite difficult to find errors in the data and the code. One issue related to Sentinel-1 is this particular coverage pattern we are having. I mean, it's really great that Sentinel-1 acquires data in a very systematic manner, but that can imply that you always have the same orbit, and you go then just 10 meters further and you have a different coverage pattern. So this is, and then when you see these kind of effects in the algorithms, you see you have a problem, but mostly we have been successful in dealing with it. Obviously, when you work on global scale, you may also experience gaps in your reference data. For example, the Hunt index is only available between 60 degree north and 56 degrees south. Yeah, and then as I showed you, for example, this algorithm challenge we have for the Tierdine algorithm. And last but not least, this definition of flooding. When is a flooding a flooding? So, I mean, some people, even if it's a yearly recurring inundation, it's called, some call it flooding, some say, well, it's just a regular recurring water. So that's certainly very challenging as well. Yeah, and it's not just challenging on a production side, it's also very challenging on the application side. So what we are producing is a scientific data product that has several novel data layers where people haven't been really used to. Normally people see maps that show flood, no flood, but really to kind of judge what the data tell you, you would have to always look into also the uncertainty layer that goes along and the masks that are provided, and not to forget environmental factors. And what I'm saying environmental factors is, for example, we don't really know where, for example, today, where the snow is wet or where the soils are frozen. We can assume that this is taking place in the northern Canada and Siberia, that this is already taking place. And in those areas, we will so low backscatter that may appear as water, but we don't have, unfortunately, auxiliary data to throw those things out. I'll thank you for the comment that there's a more complete one. yeah, and the last issue is the whole approach of that system is that you do things fully automatic without actually checking for the real flood case. So in a way, your system is always on, and in most of the cases, we will not see a flood. And now imagine that, for example, even if you have an algorithm that works for 99% of all pixels correctly, 1% will be classified wrongly. So in the end, you still struggle to see false positives. So this shows you that this is a complex data product that needs a careful interpretation. So in conclusion, we have established a worldwide 20-meter Sentinel-1 backscatter data cube system that serves both scientific and operational applications. It's now really cool because now we have made the effort, and now we have the Copernicus dam. It's really good. We have implemented 3 scientific algorithms and several base layers to depict potential flood events as quickly as possible. But obviously what's coming out there is requiring expert knowledge to make sure that one is not wrongly interpreting it. So I think what I've heard now from the MODIS presentation and the other presentations, we all have the same issues. So it's maybe a matter of phrasing it carefully enough. So SAR experts, when looking at results, will not be surprised for some of the things that you're seeing, but non-expert users, or for example, people who are used to optical data, will struggle much more. Yeah, there's a comment that there are many types of floods, fluvial floods. Yeah, indeed, there's many different types of floods that is difficult to specify. As I already had the example for the Myanmar case, I just want to show you. For example, in this case, yeah, DLR and LIST algorithm agree that there's like this seasonal flooding. In case of our TOVIN algorithm, we only detect those areas that are particular in this particular year. So here you see already the definition of this definition problem of the flooding. And here you will see the overlay of the outputs of the 3 algorithms. Thank you very much.
Thank you, Wolfgang. That was great. So you already responded to some of the questions, but there were a couple that you missed that were pretty similar from Fritz and Chandana, and they both asked about why you guys using the 20-meter Sentinel-1 flood instead of the 10-meter. Is it an issue of data storage? Have you compared the two to see what's the impact? And if you can comment on that.
Yeah, we have made different comparisons, and sometimes you may see a flood that has an advantage if you work with the 10-meter data. But overall, we feel that the benefit is not that large if you work with the 20-meter. Again, the image quality is much better and speckle is reduced. So it may be missing maybe a little of the edges, but I think the real issues are normally really somewhere else than just the very fine details. Yeah, say if you do a manual post classification of the algorithm to really be more precise, obviously it would pay off to work with the 10-meter data. But in the end, it's also a cost issue for us. As I said, we started with a 10-meter data cube. We had some years of data with the 10-meter data cube, and we've also produced a global mosaic that is at the moment being published. So it looks really great. Yeah, but keeping it for a longer time, it's challenging in terms of costs and computing system.
Any other questions on the chat?
I might have a question, and actually I have 2 questions. One on the map you're just showing, Wolfgang. I see that one algorithm picked up more or less the river course, right? Actually the one you had up, which was the light pink. Really your last. No, don't go back to all the way to your last slide.
To my last slide, okay.
The one you just showed.
With the Myanmar case.
Yes, the Myanmar case.
Yeah.
So it looks like only one algorithm picked up the river itself, right? The surface water of the river. So that's kind of confusing.
It is confusing, and I think also when we started implementing the 3 algorithms, we were ourselves surprised, you know, how different the logic is behind some workings of the algorithms. Essentially, that's the DLR algorithm, which is based on an image looking for water areas, while the algorithm from LIST and our algorithm is looking for changes.
Got you. Okay. Okay. So that explains it, because I was wondering if you could use the 3 algorithms to come up with some sort of a certainty index where you say, okay, we are very confident if all 3 algorithms agree that there's, you know, standing water, where if there's only one algorithm picking up water, then there's less chance of being actually surface water. But I guess you cannot use it in that way if you're defining just surface water.
Well, we still need to do something on this. We still need to create our seasonal reference map. So we still need to define this. That's part of the project. Yeah, it's a bit similar an issue again, like with the modus system. You have different choices of doing this. So if you would, for example, look at this case, Myanmar here, then you would see the dark red is where all 3 algorithms agree that this is exceptional water extent compared to normal years.
Yep, got you. The another question I had was on the exclusion layers you provided. One is the low backscatter, I think. And I was wondering if those layers, are they changing over time? Could they change over time? And are you incorporating that, or are those layers more static in your system?
But it would be good if they would change over time, if you start accounting for changes in the land use. At the moment, we of course have only static layers for the time being, but in the future, it definitely would be worth doing it. To update also more the information, like also this harmonic model that we have implemented for our algorithm. I think it's great. It's a great tool. But as you see, for some of the agricultural areas, we have problems. So we could maybe create the reference map more with recent data. Say, for example, you take just the backscatter images from the last, I don't know, month. To create this reference. So I think there's different ways of actually how to deal with such issues. It's of course always, I mean, scientifically you can do a lot if you have this operational system. That's where it becomes really, really tough to handle it.
Got you. Thank you.
Six new messages. I see 7. Okay, I get